Okay, yeah. So we'll be discussing special functions. So the first question that would come into someone's mind is what special functions is. Can Banjala stop writing? Okay, so the first thing that will be coming to someone's mind is what special functions is. Are they different from the normal functions we know that assign values from the domain to the range? So they are just normal functions. So they are the same functions, but functions with some interesting properties. So they are the same functions that assigns elements from the domain to the codomain. So what are special functions? So special functions are a class of mathematical functions that exhibit exceptional properties and are frequently used to solve specific types of problems across various fields of. Please, can you mute? Yeah, since you are hearing everything from my side. Okay. So yeah. So they exhibit exceptional properties. For instance, so it's not all about talking. So since we are discussing on the gamma function, I'll just give a brief introduction. So why is the gamma function a special function, or even trigonometric functions? So if you take the gamma functions, if you take the gamma function, for instance, so the gamma function is a generalization of the factorial notation. So if you have your 3 factorial, we know what it is. 6, the 4 factorial, we know what it is. So what if we want to consider half factorial, for instance? I want to consider half factorial. So we want to consider this, or we want to consider 5 factorial, sorry, I want to consider maybe even pi factorial, for instance. So how are we going to calculate that? So since pi is a transcendental number, so we don't actually know a way of calculating this without the gamma function. So that's quite obvious. So we need a special function. We need a specific type of function, a specific type of function that we generalize the factorial notation. So that function has an exceptional property. As we can see, it generalizes the factorial notation. So if you take, for instance, the Bessel function, so and Bessel function actually appears in physics. So we have many other functions. So the key characteristics. So it's not usually only important in mathematics. So in mathematics, we study properties of functions, the way the functions behave, what happens when you combine them, so or integrate them, or how the functions change. So we study all of these in mathematics, but they're actually important in science. So they're important in science. Okay. So for instance, the ODEs we have, some of these special functions are solutions to these ODEs. Okay. Let's continue then. So special functions, which include the trigonometric functions, have been used for centuries. So we know the application of trigonometric function. So it is applied in the studies of wave. So properties of wave. So we apply them in wave. So, and that's in physics. Special functions are often defined by their unique properties and integral representations. So majority of them have integral representations. They arise in diverse areas, including calculus, number theory, combinatorics, and physics. Okay. So examples include the examples include hypergeometric functions, Bessel functions, and elliptic functions. Okay. So let's continue. Okay, so the history of special functions. So we look at the historical significance. So special functions are often called useful functions. So Alan Turan gave this word, this phrase, useful functions. So, and they have a rich history. These functions have played a crucial role in mathematics and science for centuries. So notably, the trigonometric functions have been studied for over 1,000 years with series expansions known to this man in the 14th century. So a continuous evolution. So throughout history, mathematicians like Euler, Gauss, Riemann, and Ramanujan have contributed to the development of special functions. So, for instance, what we want to discuss today, the gamma function was generalized, or the factorial notation was generalized by Euler. So Euler gave the definition for the gamma function and an integral representation for it. So as well as the integral representation for the beta function. So Gauss also. So Riemann. So Riemann is very popular because of his famous zeta function, this zeta function. So, and it's popular because of the Riemann hypothesis. So the zeta function is also a special function. So when we look at this summation from k equals 1 to infinity, so this is the Riemann zeta function. So as we said earlier, these functions exhibit remarkable properties. So for instance, Euler was the first to show this this sum, which is the zeta 2, so equals pi squared over 6, and it is called the Basel problem. So what fascinated mathematicians in this sense is how we can sum up rational numbers like this. So how we can sum up these rational numbers and they end up relating to pi. So which is not, like, you cannot see pi in this infinite series. Maybe you are 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. So as you continue, so we cannot see pi in this infinite series, but it ends up converging to pi squared over 6. So these are remarkable properties that special functions exhibit. So these are the kinds of properties that they exhibit. Okay, so if you take a look at the gamma function, you look at gamma of half, and that is root pi. So it won't really make sense if you want to talk about minus half factorial, for instance. It won't really make any sense if you want to talk about this. So, but now we have the gamma function converging to of 1 over 2 converging to square root of pi. So they exhibit these kind of remarkable properties. So, and that is what we are interested in, the properties of these functions. So recent decades have seen discovery of new special functions and the applications to various mathematical areas. The importance of these functions has been recognized in combinatorics, orthogonal polynomials, and more. So from abstract to concrete. So in the 20th century, mathematics transitioned towards more abstract and existential methods. So Littlewood's perspective in the mid 20th century suggested that the era of great day of formulae had passed. So in Littlewood's thinking, he felt formulas, like, it would be difficult to bring in new formulas because as at before 2000, a lot of formulas were already known. So the gamma function that we're talking about, so it has been known since Euler's time, so which is around 1730s. So that's more than 100 years, or let's say up to 200 years ago. So Many of these functions have been known. When you study many of these books, you find many properties of these functions. So Littlewood died before 2000. So you could check him up. He died earlier than, so around 2000. So you could check that up. So Littlewood's perspective was that the great day of formulas had passed. So, however, ASCII and his other co-writers or his other writers of the book Special Functions. So they suggested that with the rise of computers and computational mathematics, formulas. So, come in, let me mute this. So they suggested that with the rise of computers, we could actually get more new special functions. So in just the past 50 years, so several new special functions and applications have been discovered, have been introduced. So the advent of computers has led to the rediscovery of beautiful, interesting, and important formulas. So these formulas are proving to be fertile ground for new mathematical insights and fruitful applications. So, and we suggest that we may be witnessing a new dawn of a new era for formulas in mathematics. So now that we have many of these computer algebra software, it is quite easy to introduce formulas than it was back then, because we didn't have Mathematica then. So it's quite faster, because you know when you're doing something, you can easily verify whether or not you are correct. So with the advent of computers, it is actually a bit easier than it used to be. So we'll move on to the gamma function. So Euler discovered the gamma function, and we denote it with this Greek symbol, gamma of x. So when extending the factorial notation. So the gamma function is a meromorphic function equal to x minus 1 factorial. So now, this English meromorphic function. So many of you would be wondering what that is. So a meromorphic function is a complex valued function. So that is defined on, so it is defined on a domain excluding finite number of points. You can say P naught to Pn, or so it will just be finite. So it could be uncountable, finite, that's it. So when we say something is finite, it's countable. So that's a meromorphic function. So more specifically, the gamma function is defined on all complex numbers, so excluding the negative integers. So excluding the negative integers. So you could write this as 0, -1, -2, -3. So the gamma function is not defined for negative integers. So it is a meromorphic function. So it is a meromorphic function. So the gamma function has multiple representations. The gamma function has multiple representations with two of the most important formulas, with two of the most important found by Euler, one involving an infinite integral and the other as a limit of a finite product. So let me attend to this person that wants to join, please. Okay, now let us continue. Okay. So the gamma function is something that appears most times in some other special functions. So it appears therein. For instance, the gamma function, I want to be more specific rather than discussing English language. So the gamma function appears in the Bessel function. So to be more specific, so it appears in the Bessel function. This is the Bessel function here. This is the modified Bessel function of the second kind. So we have these two. So it appears in the Bessel function. So it is more like a function that is ubiquitous in mathematics, something that we often see in many formulas. So, and one beautiful property of the gamma function is that if you have a formula, so not only the gamma function, so if you have a definition, for instance, if you take a look at the zeta function, for instance, now, so if you have this function, so k equals 1 to infinity, so you have k to the power of m in one of your formulas. So this is zeta m, for instance. So you could extend the definition of, if you have this appearing in your formula, you could extend that formula to this notation here, to the zeta function. Then this will become useless. Then you will just be using the zeta function, for instance. Now, these functions that you see, for instance, if you look at the zeta function, if m is -1, if m is -1, so I want to discuss what I'm discussing is this property, meromorphic function. Now, if you say this function, I've told you where the gamma function is defined on. It's defined on all complex numbers, excluding the negative integers. So you could write this in this notation, say minus, this is the natural number, so minus the natural number, and you could include it with 0. So it's not defined as 0. So if you have -half, for instance now, so the gamma function is defined here, -1/3, -1/4. So we see the gamma function is a meromorphic function. Okay. Now, for this zeta function, if m equals -2, for instance, if m equals -2, we'll have this to be k to the power of, this is not -1, it's just k to the power of m. So we would have k to the power of m. So we have k to the power of 3. So, and that series won't be convergent. That series won't be convergent. So for zeta of -2, let's use -2, then we have k to the power of 2. So if you keep on adding 1 plus 2 squared, that's 1 squared plus 2 squared plus 3 squared. So this series is a divergent, series. But then zeta of -2 is defined. So zeta of -2 is 0. But you can't see that in this definition for the zeta function. So you can't see that in the definition for the zeta function. So in general, the zeta of any negative even integer is 0. So zeta of -2, zeta of -4, -6. So it's 0, but you can't see that here. So that means we need another definition for the zeta function that we take in other values that this function cannot take in. So this zeta function is actually defined for, so this zeta function originally is defined for the real part of m greater than 1. So the real part of m greater than 1. That is, m could be a complex number, but then the real part has to be greater than 1. That's this original classical definition here. So the real part of m has to be greater than 1. But we need an extension for this function. So we have what we call the Hermite integral representation. So the Hermite integral representation provides analytic continuation for this zeta function. So that means we can have, so with that definition, with the Hermite integral representation for with zeta function, so which could be reduced to the zeta function, we could have a definition for the zeta function that we allow us to evaluate values like this. So that integral representation will provide analytic continuation to this domain, say M in C, to all complex values excluding 1. So the zeta function on its own is defined for all complex values excluding 1. Good. So when we look at the gamma function on its own is a meromorphic function. And this one also is a meromorphic function, this zeta function. Why? Because the domain, because the domain of this function is, it is defined on the whole complex plane, excluding a finite point. So, and that finite point is 1. I guess that's clear. Good. So the gamma function has multiple representations. So we primarily, one involving an infinite integral and the other as a limit of a finite product. So we primarily use the latter as the definition. So what we are saying here is, when we want to define the gamma function, we don't usually use, what you commonly know is the integral representation for that. This integral representation. So now this is an integral representation. So this is an integral representation. So what we are saying here is that we primarily use the limit of a finite product as the definition of the gamma function. So let's go on. You'll see that in the sequel. So historical perspective. Now, the problem of finding a function of a continuous variable x that equals n when x is an integer was explored by Euler in the late 1720s. So you can see that was about 200 years ago. So what mathematicians are interested in is generalizations, so analytic continuations. So what Euler was interested in looking for was a function that will be defined, that the function will be continuous, and it will be defined on what? It will be defined for values that are not integers. So we know 5 factorial, we know 6 factorial, all of these are positive integers. So he was looking for something that would generalize this, and when x is n, so then it reduces back to the normal n factorial. So this problem was suggested by Bernoulli and Goldbach. And Euler sent a letter to Goldbach containing the definition for the gamma function in October 13, 1729. Okay. Okay. So to generalize the factorial function, consider x greater than or equal to 0. So an n greater than or equal to 0 as integers. So we first take these two things to be integers, x greater than or equal to 0 and n greater than or equal to 0. We take them to be integers. Then we write this x factorial. So remember, what we are interested in is x factorial, where x is not necessarily a positive integer. So we write this function as this. Now, that notation in the bottom is something that appears very frequently in the theory of special functions. So, and this notation is where you can call it the shifted factorial. So, or you could call it the rising factorial. So, you can see how it is defined here. So, it's defined for n greater than 0. What happens is when you have this a sub n, then you have a plus 1 up to a plus n minus 1. So for instance, if you have a, so you use this bracket, don't just write it as a sub n. So when you have a sub 5, for instance, So when you have a sub 5, for instance, it equals a plus 1 up to that's a plus 2, a plus 3, then a plus 4. So this is the rising factor. As you can see that this a is rising, so it rises up to a plus 4. So now when n is 0, if you put 0 here, you have a minus 1. So we don't actually use this. We don't actually use this product for the time when n is 0. So we define it to be 1. So when n is 0. So we write this one now as, we write it in this form. So I think the work is actually, this is where the work begins. So we write that x factorial in that form. So let's show that in a bit. Okay. So this x plus 1 sub n, it remains here. So then what we are looking at is only this x plus n factorial. So in essence, you may be wondering why this is equal to this. So that's what we want to show you. So now, what will you do? Start from this n plus 1 sub x. So what will you have? You have n plus 1, right? n plus 1, n plus 2, up until n plus what? n plus 1 plus x minus 1. Are you? So, and this one we reduce to what? n plus x. That's using the definition you can see from there. So it will reduce to n plus x. So if you write this backwards, you will have, if you write this backwards, you will have x plus n minus 1. So x plus n minus 1. So up until n plus 1. Now, when you now multiply this with n factorial, what will you have? So you have x plus n minus 1 up until n plus 1 times n factorial. So let's do n plus 1 times n factorial. So you say n plus 1 times n factorial is n plus 1 factorial. So, right? So you have n plus 1, n. So what will happen is that this will keep on reducing up until 1, n minus 1. So up until 1. Okay, good. Now, this corresponds to x plus n factorial here. So this corresponds to x plus n factorial. So as you can see, x plus n will reduce until 1. So it's obvious from here. Since we've said we are assuming x and n to be both integers. So x plus n, so you say x plus 5, for instance, now. So let's be more concrete. You say x plus 5. So x plus 5 factorial. So what will happen is that this will reduce. So you write x plus 5 until you get to x factorial. Good. So until you get to x factorial. So, and this one will continue reducing x minus 1 until you get to 1. So either ways, you can write it in this way too. So if you write this as 5 plus x factorial. So, and you take this x to be what is decreasing, then you will have 5 plus x. You have what? 5 plus x. 5 plus x minus 1. 5 plus x minus 1. Then, since x is a positive integer, so what will happen? So this x will decrease until, so let's say this is 5 or 6. So 6, 5, 4, 3, 2. So 1. So 5 plus 1. Then what will you have? Then this 5 will now start decreasing. So that's what this one is talking about here. So what is happening is that we first decrease the x. So when you decrease the x, you will now start decreasing the n. Then you will have, so this one will now be like n plus 1, which is the n plus 1 you see here now. So this is the n here. So n plus 1, then you have 5, then you have 4, sorry, okay, yeah, 6, 5, so you have 3, then up until 1. So this is the common way you know it. You start decreasing the integer you see until you get to x, then x can just write x factorial here, or you start decreasing x. You say x minus 1, x minus 2 up until 1. But now, since x is an integer, you can actually decrease that x until you get to 1, then you start decreasing the n. So that's why this is equal to x plus n factorial. So you can also check that out, because I will send the material to you, then be able to check it out by yourself. So you decrease the x first. So when you decrease the x, then you decrease the n. So you get to n, because the x will decrease to 1, then you now start decreasing the n. So let's continue. So I've explained that line. So in a brief summary, what we are trying to do is we are trying to define the gamma function. So that's what we are trying to do. So we are looking for a particular representation of that factorial notation that will allow us to define the factorial forward for values rather than positive integers. So, okay, we have this. This is still here. So what did we introduce? So we introduced this n raised to power x here. So n raised to power x over n raised to power x is what? Is 1. Right? So we just introduced this here. So nothing special has happened. So now look at this limit. If you look at this limit is 1. So I won't just tell you why that limit is 1. So subsequently, well, if you read special functions by ASCII, they will just write that the limit is 1. But I still try to show you why the limit is 1 in this material that I'm using to present to you. So since this limit is 1, so we can just conclude. So since this limit is 1, we can just conclude that this is the representation for the gamma function here. Sorry, this is the representation for x factorial, pardon me. So the rest should have been discussing what that limit will be. So the nature of that limit. So how that limit will be and whether that limit is convergent. Now, I'll just give you a brief. These ones here, can't find it in our 341 explanation. We just use the integral representation to define the gamma function. I don't think that's actually bad, but we needed something that you won't have to integrate to get a representation for the gamma function. That's our aim here. So we don't need to calculate an integral of something. So we need a definition for the gamma function. Good. So I've given you the aim of what we are doing here. Now, remember that this x is not dependent on n. That's one thing. Since this x is not dependent on n, you can take your limit and nothing will happen. You can take the limit as n tends to infinity here and nothing will happen here, right? So can you respond?
Yes, sir.
Yeah, good. So we can take the limit as n tends to infinity on this left-hand side and nothing will happen because the limit of a constant is the constant, right? So now this x factorial is not dependent on n. So now, since this limit is 1, we will be very lucky, or let's say, we'll be fortunate to have a representation or a definition for x factorial, provided this limit as n tends to infinity converges. So that's the problem now. Does this limit converge? So that will be the problem now, because this limit equals 1. Nothing happens here. Then what will happen? For us to have something like maybe half factorial, what will happen? This limit has to converge. The limit as n tends to infinity. So let's see what we have for you subsequently. So questions. So these are questions I wrote down. So why did we need to take the limits? Why did we need to take limits as n tends to infinity in those expressions? So in which other mathematical context do we encounter a limit similar to this limit? So I take it majority of us are mathematics students. So this limit, there's a similar limit that occurs somewhere in mathematics. So if you know, you can write it in the chat box. I'll check it out. So a similar limit. So it's quite similar. It's not the same, but it's similar for the one I could find. The one that came to me actually. So you could find it elsewhere in mathematics, but I only know of one right now, which I wrote down here. So now, does this limit exist for any complex number x that is not a negative integer? So that's what we are talking about here now. For us to have a definition for x factorial, you know, when you took the limit here, nothing happens. Nothing happens there because x is not dependent on n. When you take the limit of, so when you take the limit of this, when you take the limit of that is 1, then this limit must converge for us to have a definition for the gamma function. So my next question was that, does that limit exist for any complex number x that is not a negative integer? So we need to take this quite serious. It's not only the gamma function that is defined for complex numbers that are not negative integers. So we have polygamma functions too. They also exhibit similar properties. And why it is so is that the polygamma functions are derived from gamma functions itself. So they exhibit similar properties. So they're actually defined on this same domain. So let's continue. So now, these are answers I wrote down. So provided that limit exists, taking limits as n tends to infinity is crucial as it allows us to eliminate. So we can eliminate that term. So when you eliminate it, okay, I don't know what's so when you eliminate it, I don't know why this is. Okay, I think it's back. Okay. That means, okay, good. I think everything is back now. So it allows us to eliminate that limit. So it allows us to eliminate this term rather in that product. So notably, the limit of x factorial as n tends to infinity has no effect on x factorial. So the limit simplifies the expression for x factorial, reducing this to 1. So we reduce this to 1 as n tends to infinity. So now I noted that we encounter a similar limit to this in convergences in distribution in probability theory. So I have defined this for you, the rising factorial. So why it is called the shifted factorial was that it was defined, that shifted factorial, when you check it on the internet, you see it's related to this Q, to that Q series. So you see it there. So it's related to that. So that's why just call it the shifted factorial. So it's related to this, so it's related to the Q analog of the Pochhammer symbol. So when you check it on the internet, you can find out why they call that the shifted factorial. But it's enough to call it the rising factorial. So we've defined that for you. Write this n plus 1, n plus 2. So up until n plus 1 plus x minus 1. Then that will be n plus x. So that limit appears in probability theory. So we will see that. So when you want to show that the binomial distribution converges to the Poisson distribution, the binomial distribution distributed with this mean n and the probability of success lambda over n. So it converges to the Poisson distribution. When you want to show this, so this is what you arrive at. So this f of x sub n is the cumulative distribution function. So we have this. Okay, I'll give you an explanation of that. Okay. Okay. So good. So I'll share another file. I actually have. Okay. 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 So this is an explanation of what I showed you earlier on. So this is the probability distribution function for the binomial distribution. Is defined this way. So it's defined this way. So I wrote that there's a product I wrote there that is equal to, that I said is equal to 1. So I could show you that. So where is it? Oh, okay. I think it's closed. So let's continue. So if we go back, there's a product I wrote that I defined as 1. And why it is equal to 1 is because n combination 0 is 1. So we need to clarify why that is 1. So when x is 0, this product here, we define it to be 1. So we need to clarify that, and I've explained it here that it's because n combination 0 is 1. Okay, good. So now the cumulative distribution function, this is how it is defined here. You will just sum the probability distribution function. Okay. It shouldn't be this, it should be mass function. That should be a typo because it's a discrete probability distribution. It should be a mass function. That's a typo. So now we have this here, then you just substitute this definition here. Good. So you know what n combination x is. So n combination x is n factorial over what? Over n minus x factorial over n minus x factorial x factorial. So this n will decrease. You know, we've assumed that x is an integer. We've assumed x is an integer. So what will happen is that n will decrease up to what? So let's pick 5 here, for instance. Now, if n is 5, so I don't want, if I use variables, it may get you confusing. So if you pick 5, what will happen is that n will decrease up until what? 4. Then you say n minus 5 factorial. So what will now happen is that n minus 5 will cancel out in the denominator, right? Oh, sorry. So n minus 5 will cancel out in that denominator. We've taken x to be 5. So n minus 5 will cancel out. Then you'll be left with n. Sorry, this should be dot, dot, dot. So n minus 1, n minus 2, n minus, so up to n minus. So this n combination x here, you can write it as n minus 1 up until what? N minus x plus 1. So when you put 5 there, you have minus 5 plus 1, which is 4. So you see that it corresponds with this. So now I've just, this one I did with you. So this one I just did with you now. I've done it with a variable now. So I've removed the number and replaced it with a variable. So you should understand that now already. So this is over x factorial here. So let's quickly move on. So you can see that you just need to pay another attention. So you can see that this is similar to the rising factorial we discussed the other time. So the other time we had n, okay, we used a, we say a plus 1, a plus 2 up until a plus n minus 1. But now this one is n minus 1, n minus 2 up until n minus x plus 1. So now this factorial that you see here now, or sorry, this product that you see here now is called the falling factorial. So that's why I said, where else can you find this? So you can see we find it in convergences in distribution in probability theory. You find the falling factorial here, which is quite similar. That's why I used nuance, so like quite similar. So I skipped all of these steps, which I should have perhaps shown on the board. So I skipped it in the other slide. So this was where I just continued from here. So, but now this is the explanation here. So when you set P to be lambda over n, this is what you have here. So now when you look at this one and you take the limit as n tends to infinity, by indices, you can split this. Then this one is not dependent on n. So you can just take the limit as n tends to infinity here. Then you have 1 minus 0, you have 1 here. And this is just the exponential of minus lambda, if you remember. So this one is now e raised to power minus lambda. This is lambda to the power of x, and this is x factorial. So you can now bring everything like this now. And now we just need to consider this limit. So now let's continue with this explanation material. So let's consider that limit. Okay. I think it should be in the next, it should be in the previous one that we were using. Okay. Now, so this one means that xn, the random variable, is binomially distributed. So it's just a language. So it's binomially distributed. And this was the product I was telling you about. So which was why I was explaining why it was 1, or why it was defined to be 1 if x is 0. So I've explained that already. So now when we want to show this, so in all of that file, you will see that we wanted to show this. So now what we ended up having is this. And what you can see here, you can see that we have this n minus 1, n minus 2 up to n minus x plus 1. So that's our bone of contention. That's what we are interested in. So let's continue. Okay. Now, the limit is easy to evaluate for x equals 0. Okay. Let's go back. Oops. So the limit is easy to evaluate for x equals 0. Why? We've defined this product to be 1 from here, and I've explained why it's 1. I said n combination 0 is 1. So we've defined this product to be 1 if x is 0. So what will you have if x is 0? 1. What will you have if x is 0? What's n raised to the power 0? 1. So you have 1 over 1. So this limit will be 1 if x is 0. So that's like trivial. So what if x is not 0? What if, and now we said, remember in our first assumption, we said x is a non-negative integer. When you say non-negative, so non-negative means is non-negative, okay? And it could be 0. That's the meaning of non-negative, not negative, because 0 is not negative, and neither is 0 positive. So when you say non-negative, you are including 0. That means we are looking for all integers that are not negative. So when you say non-negative integers, you can say non-negative real numbers. So whatever you want to say. So a non-negative set, for instance, is just what? The positive part of that set, including 0, because 0 is non-negative. So now we've said x is non-negative. So I've shown you that x equal to 0, at x equal to 0, that limit is 1. So assuming x is a positive integer, now we've dealt with 0. So what will x become now? X will be a positive integer. It will no longer be a non-negative integer. So now assuming x is a positive integer, now we can distribute this n. We can distribute it across the numerator. Okay? So we can distribute it across the numerator. Now you need to notice something. We have n minus 0 here. Since we know x is a positive integer, is 1, it could be 2, it could be 3. So now 0, 1, 2, up to x. So this is n minus, if you put in brackets, x minus 1. So 0, 1, 2, 3, up to x minus 1. So how many numbers are there? Can somebody answer that? Hello?
Yes, we are there.
Huh? How many numbers are between 0 and x minus 1? If x is a positive integer. Okay, the people here said x numbers. So yeah, so they are x numbers. Okay, they are x numbers. So that means from here to here now, we have x numbers. That's the meaning, because we are multiplying this x times. That's the meaning. So now, and we are multiplying n x times. That means you can distribute. So that means you can distribute this n across this numerator. What will you have? N over n, n minus 1 over n. So if you will do that until you get to here. So 1 minus what? 1 minus x minus 1 over n. That's the meaning. It means you can distribute that n across that numerator. So it's quite clear. So n over n is 1. So now when you take the limit as n tends to infinity of this one, what will you have? 1 minus 0. So you keep on multiplying 1 minus 0, 1 minus 0, until what? When you get here, this one too will be, because this limit is 0 when n tends to infinity. So you have 1 minus 0. So when you multiply everything, you have 1. Good. So now this is for the falling factorial. Let's look at the rising factorial. We have n plus 1, n plus 2, up until n plus x. Now, this is n plus 1 to x. So from 1 to x, how many numbers are there if x is an integer? Huh? So x numbers. If x is an integer from 1 to x is x numbers, and we have n to the power of x in the denominator, we can also distribute the n across the numerator. So when you do that, what will happen? You still have 1. So now you can see that the rising factorial and the falling factorial, they exhibit this similar property on limits. Is that when you divide it by n to the power of x, both the limits are 1. Okay, good. So we can define the rising and the falling factorials here. So we say the expression n plus 1 up till n plus x, we denote it as this, n plus 1, then you put it like a raised to the power of x. So it's n plus 1 to the power of x bar, or we use this notation. So now, when you read Wikipedia, for instance, Wikipedia doesn't use this for rising factorial. Instead, it uses this for falling factorial. But in the theory of special functions, this is what we use. But I don't know why Wikipedia chose to use this for falling factorials. But what you will be doing it just depends on the material you'll be reading. But in special functions, we use this for rising factorial alone. So n plus 1, so we write n plus 1 sub x here with the bracket, or n plus 1 to the power of x bar. So for falling factorial, it will be, we underline the x. So now when you replace this with n minus 1, and you have a. When you replace n with a minus 1, you have a sub n, and you replace x with n. So I want to just simplify it to this. I want to define a to the power of n over line. So that is a plus a times a plus 1 times a plus 2 up till a plus n minus 1. So, and we define this to be 1. Good. So now, a very good property is that this is the same domain on which the gamma function is defined. Okay? So the gamma function is defined on this domain. Okay, good. So now, the same for the falling factorial. So we call this the rising factorial, and we call this the falling factorial. So let's move on. Now, the limit. So the existence of the limit. This is what we wanted to take the limit of. We want to discuss. Does this limit exist? Now, this limit exists. Why? Because we can write this, sorry, the limit of this expression exists because we can write this expression in this form. Now, this symbol means product. This symbol means sum. In Greek, this is capital pi. Capital pi. You know yours, this is the small pi. Why this product notation is capital pi? Why this one is the sigma, the capital sigma. So capital sigma for sum, we have small sigma. So this is small sigma, this is capital sigma, this is capital pi, and this is small pi. So we use this capital pi for product. It means when j is 1, multiply with when j is 2, multiply with when j is 3, up until j equals n. Good. So now, this particular expression here, when you take this, like when you want to take the series of this one now, 1 over 1 plus x. So the first term is what? You say 1 minus x. That's clear. So 1 minus x plus x squared, blah, blah, blah. So plus x squared minus x cubed. That's the Maclaurin series for this. So now when you multiply the Maclaurin series for this one, say 1 minus, so replace x with x over j. You have 1 minus x over j, right? Let's just, we'll stop at x squared plus x squared over j squared. Now I will explain this. So these are things that I should have done on the board, but I did it in the other explanation note. So I will explain the meaning of this. So you just, after I explain this, then I will explain this, the meaning of this in the explanation note. So with the explanation rather. So this is x squared over j squared. So let's stop here for this. You know, this is 1 over 1 plus x. This is how it looks like. Replace x with x plus j here. That's what I did. Now, let's multiply with this one also. Multiply it to x squared. Multiply it to x squared. So 1 plus x to the power of n is what? Is 1 plus nx plus n times n minus 1, right? So times x squared, you continue like that. So now replace x with, replace n with x and replace n with 1 over j. So what will you have? You have 1 plus, so we are replacing x with, where is it? With n. So we have 1 plus, and we have 1 over j times, that's our n now. Our x is what? Our x is n. So 1 plus n over j. Oh, sorry. This n here is the power, so it's x. So 1 plus x over j plus x times x minus 1. X times x minus 1, right? Over 2 times what? 1 over j squared. Is that clear? Good. Now, it's quite funny. Let me write it clearly. So we have 1 plus, it's just a basic series expansion. It's not something special or difficult. Don't look at it like it's one difficult thing. So 1 plus x over j plus this. Now look at this now. Multiply 1 times this. What will you have? 1 plus x over j plus what? X times x minus 1 is binomial expansion, yes. Over 2j squared. Now, the next one will be multiplying minus x over j with this one. What will you have? Minus x over j. So you can just stop there. Okay? You can stop there. Minus x over j will cancel out. Okay? You know, when you multiply again, you'll be having like a cube term or something. So you can stop here now. So what we have? We'll have, you can see it here now, 1 plus x times x minus 1 over 2j squared. So in essence, again, what we are doing is just our normal binomial expansion, please. It's binomial expansion. That's what I use. So when you expand this is what you have. So, and therefore we can conclude that the limit, when you take this, where is it? The limit as n tends to infinity from here now. So since this is the first term here, then if j is 1, you have this, multiply it when j is 2. So we can conclude that the limit exists. So let's look at this explanation quickly. How is n factorial times n to the power of x equals x plus 1 sub n? So that would be a question, over x plus 1 sub n. How is it equal to this expression? So let's go back to so now this is the explanation here. So let's further explore this expression. So you will observe this. So what you've been doing since I don't know, since ages, you're realizing 5 factorial as 5 times 4 times. So now you need to be familiar with infinite series, finite series, finite infinite series, and also finite and infinite product. So it's important. It's important in the theory of special functions. Why? I'll give you just one instance. The beta function, which we'll treat on Friday, God willing. So the beta function on its own, we can discuss analytic continuation for the beta function by using an infinite product. So finite product, infinite product, finite series, infinite series, these are things you should be familiar with, should know those notations. So this is the product notation for x factorial. This is a dummy variable. You can use k if you like. Say when you multiply, when k is 1, when k is 2, you multiply it up until n. So we can use this to represent the n factorial. Good. So we can mark this out. We've dealt with n factorial. Now, this is x plus 1 sub n. So, and this is the rising factorial, which is x plus 1, x plus 2, up until x plus n. Good. You can now replace this 1, 2, 3, and so on. You can replace it with k or j if you like. So, we want uniformity. So, we replace it with j. Now, we now multiply the product. Sorry, now multiply this time. We say multiply x plus j when j is 1 to n. Say multiply j plus 1, x plus 1, x plus 2, up until x plus n. So we've used this notation for x plus 1 sub n. That's quite interesting. So n factorial over x plus 1 sub n, what will you do? You will combine this one and what? And this one. Is that clear? So you will combine, this is n factorial. Now, this is what? This is this product. Unlike series, if you have a sigma up and you have a sigma down, you have a sigma up and you have a sigma down, you cannot write it as one sigma. Good. But for product, if you have a product notation up and you have it down, you can write it as one product. Why? Because if you have 3 times 4 times 5, they are of the same length. And you have 7 times 8 times 9. You can just say multiply 3 plus k. Multiply 3 plus k. So you can say multiply 3 plus k from k equals 1 to 2. Right? And you can say multiply, so you can use this product notation, say k equals 1 to 2. And you can say multiply 7 plus what? 7 plus k. K equals 1 to 2. 1 to 2. And also you can just write it together, say multiply 3 plus k over 7 plus k. So multiply it from k equals 1 to 2. So you can write it in this form. So what will you have for this? 3 plus 1 over 7 plus 1, have you multiplied by what? So which is 4 over 8 times. So I'll just give you one. I'll say, oh, oops. No, it's supposed to be from 0 since I started from here. So it will be what? 3 plus 0 over 7 plus 0. Say 3 over 7 times what? 4 over 8 times 5 over 9. So we stop there because k is stopping at 2, 5 over 9. Why it is so is that when you have a fraction a over b times c over d, is the same thing as what? AC over bd. But when you have a over b, okay, plus, let me see, plus c over d. So it's not equal to what? A plus c over b plus d. So something like this. So, but is this really useful in this discussion? I don't really think so, but this is quite useful. So now you can just take out each fraction and multiply it. Or you multiply the numerator on its own and the denominator on its own and you divide. So that's a special property of the product notation, is that when you have, and the thing is, what you must observe is that what? They must be of the same length. You can't have n plus 1 here now. If you have n plus 1, you will need to stop it at n and write, maybe n plus 1, you write x plus n plus 1, multiplying this. So they have to be of the same length before you transfer them to one location. So let's continue. Okay, good. Now you can write it under one notation. You can write it under one product notation. Say you want to do the product of j over x plus j. You get it now? So I've explained that already. So now this is quite basic. You can divide everything here by j, which is j. So you can divide this over j. Nothing changes. So j over j is 1. So x over j plus 1 is what we have here now. So this is reciprocal. This is 1 plus x over j reciprocal. So we've dealt with this. So now, what have we dealt with now? We've dealt with n factorial over what? Over x plus 1 sub n. So we've said that is equal to what? Is equal to this. What is remaining? We need to discuss this product. So the product of this. So that's what we discuss in the next slide. So this is also useful knowledge. Okay, let's continue. Now, this is the last thing I say we are going to discuss in that as far as that product is concerned. Now, to explain this, this is simple fractions. When you have 1 plus 1 over j, what is that? It's j plus 1 over j, right? That's quite simple, elementary. So now, when you raise this to power of x, what will happen? You can raise this to power of x, and raise this also to the power of x. That's what we have here now. Now, this is like a telescoping product. Good. So it's like a telescoping product. How? When j is 1, what will happen? So you see, say you have 2 raised to power x, 3 raised to power x, 4 raised to power x. Then when j is n minus 1, you will have n raised to power x. When j is n, you have n plus 1 to the power of x. Now when you start multiplying j to the power of x here, you have 1 to the power of x, 2 to the power of x. So up until what? N to the power of x. Now what will happen is that 1 to the power of x is 1. So this is quite excluded. Then you start canceling. Okay, there's a 4 mistake. So you cancel this. So you cancel the 3, you cancel the 4, you cancel the n. So what you'll be left with is n plus 1 to the power of x. So now we've shown that this product, so you see it's quite remarkable now. So you've shown that this product, this n plus 1 to the power of x, you can write it in this form. So this is a finite product. Good. So now, since we have shown that this is this, and this is n plus 1 to the power of x, this product expression, let's look at what happens next in the next slide. So now if you now introduce this n plus 1 to the power of x, it's like writing 5 over 5, like rationalizing. Good. You can write this one, this is equal to n plus 1 to the power of x from what we've shown. So if you write this as n plus 1 to the power of x and you write this here, so it's like canceling out an expression. Good. Now we'll do a kind of sweet rearrangement. Rearrange n to the power of x and n plus 1 to the power of x. You have this. Then write n factorial over x plus 1 sub n. Now we have this product. Okay, good. Now we showed that this is equal to this. When we have 1 plus x over j, I said reciprocal, then okay, we've shown this already. So now this is equal to this product. So you're having one product from j equals 1 to n, another product from j equals 1 to n. You can just pick one of these notation. Why? It's just product. If you have, maybe you're having one family multiplying each other here, you're having another family multiplying each other here, you can multiply everything together in one bracket. That's what we are doing here now. So you write them under one product notation, and we have this. Then what will happen? You can write this as n over n plus 1 to the power of x. So now we've shown this expression now. So we can go back to our discussion and round up. Okay. Now let's define the gamma function. We are rounding up. So now this infinite product converges. Well, you could try to look for more explanations why it converges. If you want to get or as you are home, you can try that. So why does it converge? So we've written this as this expression here. So some say it's obvious, but it's really obvious for some of the people I'm talking to. So you could try to investigate that if you are not still convinced that if you replace this with this here now. Maybe you take this product as j equals 1 to n, and you take the limit as n tends to infinity, that this converges. So you could try checking that out. Okay, so now we can define the gamma function. So we define the gamma function as just that limit. So you define it as just this limit. What we've been doing so far was to show that, okay, this limit exists. Now, that x factorial, replace it with this. Now, this is also capital pi, but we use it, well, in LaTeX, you implement this one as capital pi. And that one, you write PROD, like product, where two of them are capital pi's, but this one is smaller than that one. They have different functions. So now, you see pi of x equals this, and we call this x factorial. And we say it's defined for all complex x not equal to what? Not equal to negative integers. Good. It's not equal to negative integers. Now let's define the gamma function. So let x be in a set of complex number excluding non-negative integers. Sorry, excluding negative integers and 0. So what will happen? Then the gamma function is defined this way. So what's the difference between this notation and this notation? Okay, those of you that are here, can you answer that? The difference between this notation and the gamma function. So what do you observe? So there's a shifting. So what did they shift? They shifted the value of x. Thank you. So this x was shifted to x minus 1 here. This x was shifted to x minus 1 here. Good. Now, this is due to Legendre. Okay, there's electricity. Okay, this notation is due to Legendre. Why this one is due to Gauss? But we prefer to use yeah, we prefer to use the gamma function. Why? So you will see that in the when we are discussing the beta function, why we prefer to use the gamma function. So what is the equivalence? Say gamma of x is equal to this pi of x minus 1. But we don't use this, we don't use this Gauss notation. We use what? We use Euler's, sorry, we use a Gauss notation. So remember from the beginning, we said Gauss. Okay. Okay, sorry. So this is due to Gauss. Why this is due to Legendre? Let's continue. So you can use that definition so you can use the definition to show this. So these are things that you can do by yourself from the product notation. So can somebody try it here? Yeah, you use the definition that limits to show that gamma of x plus 1. So we call that the recurrence relation for the gamma function. Huh? So if you do replacement, what will happen? So we have gamma of x plus 1 equals k factorial. Okay, limit. Let's just write LIM. Sure. Say limit k factorial k to the power of x over x plus 1 sub k. Good. So write this x plus 1 sub k now. So if you write this out, what will you have? X plus 1, right? Continue now. X plus 2 up until what? X plus what? Are we using n? So up until x plus k. Now, if you introduce an x here, what will happen? if you have x times x plus 1, right, up until x plus k. So what will this become? So it will become, do you think so? So you have x, so that means this is this here, x plus k minus 1. You get it now? So that means from these two relations, what can you notice? You can notice that x plus 1 sub k is equal to what? X k over what? Over x times what? Times this last stuff here. X plus k minus 1. So now let's put it back in this definition for the gamma function. Okay, yeah. So if you put it there, what you have? When you take the reciprocal, you will have what? So you will have it equal to x times what? X plus k minus 1 times k factorial times k to the power of x over x k. Exactly. So there's a limit behind. Okay, so we have this here. So now we want to deal with this limit here. So if you write this, so we are having x is not dependent on the limit. Is that clear? So we write x. So we write x plus k minus 1 times k to the power of x. So let's do this over k. So if you do this over k, what will you have? Hello? Okay, let's split this out. What I'm doing now is that I want to do minus 1 here. Okay? So, and if you do, oops. Okay. Okay. If you do over k here, let's do over k of that first. So if you do that, what will you have? This will be 1. So because these two will be 0 because they are over. So that's clear. So if you have over k, then this one will be k plus 1. I mean, k to the power of x plus 1. Then what will you be left with? We left with x times this limit. Okay? K factorial some minutes. Okay, so from here we wrote x plus 1 sub k in terms of this. Okay, over what? Over x sub k. Okay, but it's not yet corresponding. Yeah, so we have x here. X in the numerator. Okay, wait. This is k to the power of x here. Okay. So if you have k to the power of x here, wow, there's another way to go about this. So if you write this k factorial as k times k minus 1 factorial. So what we have is what? We'll have this one to be k minus 1 I'm coming.
I just x plus k. X plus 1 sub k. X sub k k.
I think this is okay now. This one, that's okay. But I want to try it another way. So like this now, we're not able to prove it this way. So we could try from this k factorial. So if you write this k factorial as k, okay, you say k times k minus 1 factorial. That's the cleaner. What's the mistake?
X plus k minus 1 should come to x plus k.
Oh, oops. Yes, that's true. Okay, that's true. Yeah, I just saw that. Thank you. That's this one is actually behind it. So let's, oh, yeah. So this one is to stop at x plus k. Why this one is to stop at x plus k minus 1. Okay, that's true. That's true. So in essence, what you have for x plus 1 sub k? You have x. Okay, thank you. So we have x sub k over x plus k. That's what we are going to have. So we'll have this. We'll have x plus k here, not x plus k minus 1. Where's the duster? Okay. So we have x plus k here. So the aim is to get a x minus 1 up. That's the aim. So we have an x plus k here multiplying this x here. So, and this is k to the power of x. So we want k to the power of x minus 1. Okay, let's try it out. Let's do some control. So if you write this as k to the power of x plus 1, okay, and you write this as k, then we'll have 1, right? Then we'll have k to the power of what? K to the power of x plus 1. We'll have k factorial, and you have what? X sub k. So if you replace k with k minus 1, what will happen if you replace k with k minus 1? You have k minus 1 factorial, okay, which is not quite cute. It won't make sense that way. Okay, let's look at that k factorial. What can we get from k factorial? We can get k times k minus 1 factorial, right? Okay. I borrowed you know, so maybe you pause for some minutes or something. Some minutes, please.
Okay. Ah, that's
Maybe we just round it off since we have 4 more slides. Then I maybe check it back and get back to you on that. So that will be better than. Or we could look at it before we round up. So let's do the rounding up before, because we have 4 more slides. So we show this limit for x being a positive integer. Does this limit hold true for, so for x being a non-negative integer, where x equal to 0 was trivial? So does this limit apply to other values of x that are not integers? So you could, that are not positive integers. So you could try that out. Could use Sterling's approximation for the factorial if you want. So we have this Weierstrass expansion. So the Weierstrass product for the gamma function forms the basis of the digamma function. So this Weierstrass expansion for this Weierstrass product for the gamma function. So it's a very, very important one. So, and it is from the definition of the gamma function so it's from the definition of the gamma function we get this. And now there's a constant you need to take note of. So this constant is called Euler's constant. So, and it's 0.5772, so 4 decimal places. So, and that's Euler's constant defined by this. Now, this sum is called the harmonic number, Hn, the nth harmonic number. So the sum, when you sum 1 over k, so this is denoted Hn, it's called the harmonic number. So the limit as n tends to infinity of Hn minus the logarithm of n is called the Euler's constant. So good. So that's called the. So and how do we get this Weierstrass product? So we get it from the definition of the gamma function. Let's look at the definition of the gamma function. So 1 over gamma of x is equal to this product. Let me go back on page 1. Started. That's better. So now, okay, when you take the reciprocal of that definition for the gamma function, this is what you have. Now, the same argument, similar arguments that we've been making. So now you look at this from 0 to n minus 1. From 0 to n minus 1 contains n integers. And we have n factorial down. So when you have n factorial, say 5 factorial, we have 1 times 2 times 3 times 4 times 5. So we have 5 positive integers. So we have 5 positive integers. So, and here we have 0 to n minus 1, which is n positive integers. So all you do is that you split this n across the numerator. So all you'll be having is 1 over x, sorry, 1 plus x over 1. So this one will be over 1. So you will continue that way. So we have x plus 2. We have x plus 2. Thank you. So x plus 2 over 2, right? So until we get to what? X plus until we get to what? So there was quite something that made me laugh. Well, if you look at this is n factorial. So we said 0 to n minus 1 contains n integers and n factorial contains n integers. So good. So that means if we start this one from n, you get it now. So if we start this one, say we want to number 1. So all we will have is what? So we will have n1 to n minus 1, right? So and that will contain how many? Okay, this one actually contains n minus, so it contains n integers. So this one will contain n integers, right? Because from 0 to n minus 1, say 0 to 4 is 5 integers, right? So from 1 to n minus 1 will contain what? N minus 1 integers, just like you are numbering 1 to n minus 1. Good. So now that means there will be okay, you have x plus 1 over 1. So you will stop at where? X plus
n minus
1 over n minus 1. Is that not true? Okay.
Yes.
Good. So we have this from x plus 1 over 1, from x plus 2 over 2, we have 1 plus x over 2. And here we have 1 plus x over 1 plus x over n minus 1. So that's clear. So there's now an introduction of one extra term, 1 plus x over n. So you can introduce this. Why you can introduce this is that, because what I'm trying to explain is that from here you stop at 1 plus x over n minus 1. So how did this 1 over x plus n come in? You can actually introduce it. Why? Because when you take this limit is 1. You get it? So when you take this limit as n tends to infinity is 1. So originally you should stop at n minus 1. But it makes no difference when you do that, because the product of the limit is the limit of the product. So you can just introduce that last one, since that last one is 1. So in essence, I've explained what happened to this. So it should be n minus 1, but if you stop at n, there's no problem. Okay, good. So what's the next thing to deal with? So the next thing we can deal with is this n raised to power x. So this is actually n raised to power x, I mean. So e raised to power minus, so we have e raised to power minus what? Minus the logarithm of n to the power of x, so which is e raised to power the logarithm of 1 over what? N to the power of x, which is 1 over n to the power of x. Okay, good. So now that means there is one n minus 1. So sorry, we only dealt with n to the power of x here. So we are having n factorial over n left here. So, and this is n to the power of x. So this one will be what? N minus 1 factorial. It's clear now? So this is what I'm saying in essence. This one is n minus 1 factorial times what? Times n to the power of x. So now n minus 1 factorial will contain n minus 1 terms. Is that clear? So that means you can distribute n minus 1 factorial across all of this from 1 to n minus 1. So it's still the same argument, is that this will still stop at what? X plus n minus 1 over n minus 1. But introducing this last one doesn't make any difference because that limit is 1. So you still have the same thing. So we've written this in this way. So now write this as a finite product. So what can you notice? We can bring out the x is not dependent. X is not dependent on the n. We can bring out the x here now, and we have e to the power of x. Where is it? Okay, good. Another thing has occurred here. So where is it? So we have 1 plus x over n that we are multiplying from. I've used the wow. Like there are some notation issues here. This n that I was using. Yeah. Well, it doesn't really. Well, it's just a dummy variable. Let's look at this. So now if you look at this here, the limit is still here. So nothing has been done. So this is the e raised to power minus x log n. So you can see it here. It's obvious here. So now the remaining thing that I have to explain is this e raised to power x, e raised to power x times what? E raised to power x over 2. So you need to pay attention for this one. Say up until e raised to power x over n, right? Good. This is the e raised to power minus x log n here. So now if you look at this one here, when you multiply from any, this dummy variable I use, there's a problem with it. Okay? It's a problem with it. Maybe you can use k equals 1. You can use k, you can use k, you can use j also. It should be a typo. So if you use j that we've been using all through, use j here. Use j here. So now when you multiply this product, when this one is 1, all you have e raised to power minus x. Is that clear? When that one is 2, you have e raised to power minus x over 2. Right? Until you get to what? E raised to power minus x over n. So you can change this to j. I will make those changes before I send it. J or k, anyone you want, any dummy variable. Should be a typo. So what will happen? This will be 1, this will be 1, this will be 1. So there's no problem, right? So we can now write this as what? As our gamma. So that is the Euler gamma. So we see that is the Euler's constant. So now this is Weierstrass product for the gamma function. So if a problem you could think about is why it converges. Though these are old problems, but could do some new analysis on it. It's possible, like post it on Stack Exchange or any other platform like Stack Overflow. So they are old problems, but doesn't mean that you can't bring anything new out of it. So you could consider convergences of distance. So you could try studying them. So why the infinite product converges. Now this forms the basis of the digamma function. Good. So if you take the logarithm of this, another beautiful property of I think we are done with this slide. So another beautiful property of the product notation is that when you take the logarithm of a product, what will happen to become the sum of the logarithm? Good. So when you take logarithm on both sides and you differentiate it, so we have what we call the digamma function, okay? So this digamma function is defined to be the logarithmic derivative of what? The logarithm derivative of the gamma function. So, and it's also a meromorphic function defined on all complex numbers, excluding the set of negative integers and 0. So these are very interesting functions. Would also bring out something new from these functions. So the last paper I wrote was on, okay, the last two ones was on infinite series. So a class of series involving the digamma function. So the digamma function was a summand in my series, then I could get some proof forms for those infinite series. So you could try taking the logarithmic derivative of this Weierstrass product, and you have the digamma function. So I think that would be all for now. So let's finish by 5 o'clock. Maybe we'll go back to this limit and see about it. So we end by 5.
Okay. So the I don't want to.
Oh, which one is supposed to be? Please, you give us some.
See, it's x of this.
Okay.
You write it out. See, x plus 1
Sub n.
is equal to x plus 1, x plus 2, equal to x plus 1. So an x of n is what? X plus 1, equal to x plus n minus 1. So and there is a x plus n minus 1 there. So you say x plus 1 sub n equals what? Equals so x plus 1 equals x plus 1 upon 0, x plus n minus 1 times x plus n, right? So, and this is equal to what? So if you introduce an x here, right? So you have x plus n by x here, right? So we would have this as x plus 1 sub n equals x sub n times x plus n by x. Okay, that something else. Yeah, this one. Okay, I brought them together. Oh. Okay, so all we have is limit as k times to the same. Okay. The k factorial. So a to the power of x over x of n, x plus n times x. So this x now. Wow. Okay. So we've figured out the issue. So that would be for my end was a mistake. So if you take things step by step, then I wouldn't have made that mistake. So this is it here. We want to prove the recurrence relation from this infinite product. So and the mistake was from the origin of that mistake. So where though the intuition of comparing this with x sub n is also correct, but the mistake from where I was supposed to stop caused the issue. So you have this x plus 1, x plus 2, up until x plus n. You have x sub n. Oh, you must put that bracket. If not, you are writing something else. So x
sub n is what? X times x plus 1. So this is perfect now. It's actually simple. Just the mistake. So until x plus n minus 1. Now, it's a problem of identifying where this stops. So x plus 1 sub n equals x plus 1 up until what? X plus n minus 1 until x plus what? X plus n. So if you introduce a x here, you will introduce the x in the denominator. Good. So this one, you will write this one as what? X of n. Thank you. And then you write this one as what? X plus n, which is what is remaining there over x. So my earlier mistake was bringing these two together. Oops. So gamma of x plus 1 will now be what? So like this, the limit is straightforward. So it's very easy because we just need to bring out a x minus 1. Then, okay, let's look at it. Say k factorial, then k to the power of x, right? Over, replace this one with x plus 1. So we will have what? X times what? X sub n. Sorry, x of k. We are using k in the limit, not n. Times what? X plus k. Now, to treat this limit, just introduce a minus 1 here and introduce a k. Then this will be 1. Is that clear? So what will you have? You have limit as k tends to infinity of k over x plus k equals what? Equals 1. So people that are here should know that now. So the limit is just, you write 1 over what? X over k plus 1. That's how you write it. Then this one will tend to 0. Then you just have 1. So since that one is 0, what will you have now? You have x times what? Times the limit k factorial times k to the power of x minus 1 over what? Over x of k. And this is what? The definition for the gamma function. So you can see we didn't have to integrate, as you'll be taught in some of your regular courses where we use the integral representation as the original definition for the gamma function. So that's also correct. But the definition for the gamma function is this product. Sorry, is this limit. And this limit is an infinite product. Because what is in the denominator is a product, right? Yes. So and with this definition, we have you can get the digamma function. So a little teaser on the digamma function is that when you look at the gamma function is rapidly increasing. So the gamma function is rapidly increasing. Say you have 10 factorial is massive. You get it now? So 10 factorial is massive. So when you look at where's my calculator? When we look at 10 factorial, we have 3,628,800. So that's 10 factorial. So it's actually massive. And it's because of the decreasing property of the gamma function that makes the exponential series to converge. So when you look at something like this now, say this sum, so you just need to observe some of the nature of this infinite series. When you look at this sum now, you have k factorial, right? And you have this from 0 to infinity. So this is the exponential function. Now this is 0 to power x, and not k. K is a dummy. So now, if you look at this series now, it's because when you have something like 5 here now, 5. So when you have something like 10 here, what will happen? This one will decrease. So the denominator is decreasing faster than the numerator will ever increase. You get it now? So when you're not talking of maybe 100 factorial, you know 1 over 100 factorial is approaching 0 faster. So that's why this one converges. That is part of why. But when you now remove this factorial, if you remove this factorial now, this will become what? What series is this? Can somebody answer that? This series, what is this? We now want to, I've removed the factorial. So what series is that? So this is minus logarithm of 1 minus x. So this is minus logarithm of 1 minus x. Good. So now if you put 2 here now, for instance, what will happen is that we divert, the series will divert. So this k does not decrease faster than this 2 is power k increase. You get now? Say you have 5. What will happen? You have 32 over 5. But if it was factorial, you will have 32 over 5 factorial. And 5 factorial is larger than 32. You get it now? So these are things you should notice about infinite series. So the denominators, these denominators that you see here, they actually matter a lot. And that's why the exponential function is faster converging than. So this is just the logarithm function. So the gamma function is this normal gamma function. It's not so interesting again because it's a very, very good problem. So I don't know of anything new that someone can bring it, except you can do some analysis on those infinite products. So perhaps you could get something new. But what you can get is like series involving gamma function, integrals involving gamma functions. We'll get something new from those. And the gamma function or the digamma function is quite very, very useful. It's quite very useful. So look at that. And again, is another last thing is the beta function. Beta function, I see it to be more useful than the gamma function. So the beta function has this gamma function representation. You say beta xy, right? So equals what? This is the integral. Now, you need to pay attention at this point. You say this gamma function has a definition. You get it? That's the definition. But now we refer to those beta functions as beta integrals. You get it? Because we just define them on that integrals. So from that integral, you can consider them as family of integrals. So from that integral, this definition, okay, this is y. So you can represent it as what? Gamma x, gamma y over gamma x plus y. So Euler was also was it the first? It should be the first. So Euler was the first to show this. So we refer to this gamma function, the first integral for the gamma function, we refer to it as this integral. So you see it didn't appear throughout this presentation. So we refer to this integral for the gamma function as the Eulerian integral, first integral. So we refer to the beta function known as the second integral. So as the second Eulerian second integral. So Euler was actually very smart in proving this. So if you read the books, you see the remark they made on Euler was very, very impressive. So how he was able to come about this was by integrating by parts. So by replacing this with y plus, okay, no. From the book I read, it was stated that their approach was quite different from Euler's. So, but the way of proving this is by replacing this with y plus 1. Then you have a 1 minus t here multiplying 1 minus t times, sorry, to the power of y minus 1. Then you expand, then you have two difference. So you have a difference of 2 terms. Then you do integration by parts. Then you have a recurrence relation. So from there, you can be able to take your limits. So Euler was very smart in proving this. And now this beta function is very useful in infinite series. So there are many infinite series. For instance, when you look at the Bessel function, for instance, the Sonin integral representation was derived by making use of the beta function. So we round up here. So see you Friday. Now. So thank you for listening and have a nice day.
Thank you very much, sir.
Yep.
Thank you very much.